Welcome to another episode of All the Ideas. I'm Dan Servo, this is Douglas Bebb, and, well, we're traveling this week, and we're in Claremont, California, and just got done with SIAM, Society for Industrial Applied Mathematics.
For all of you not in California, the weather is beautiful this time of year.
Yes, better than Arizona.
Yeah.
Well,
So we're enjoying a little bit of relief from that. Definitely a little more humid than I think we're used to. But we want to talk about what we did at SIAM and some of the events that happened there, some of the people that we met. And it was really just a busy day, all day long, starting from early in the morning and ending at 10 o'clock at night. So it was a very busy day.
yes, it was. It was definitely very mathy, to say the least. I know Madfellows itself has presented two things there. We presented, what was the first thing we presented?
Well, it was Scott Little did isogeometrics and transformation optics to describe metasolenoid singularity. Electromagnetic singularities. So,
Okay. Yeah, that was the metamaterial stuff we've been working on that he's kind of taken off and added string theory to, and hopefully we can create a real nice real life analogy to creating a singularity.
Yeah, I think from what Scott Little's managed to put together, his next step, he's going to be looking at putting together an actual paper for that, and then probably beginning work designing some experimental verification on that down the road.
That's what I'm looking forward to. I'm definitely looking forward to making the actual experiment.
I think that's a little bit more of our specialty, so we'll definitely be able to contribute to that portion even more than the first part.
And then this was also your first time presenting anything at SIAM.
Yeah, in fact, it was not just my first time presenting, it was my first time at any of these events. So really it was, didn't know quite what I was getting into, so trying to just make sure that we were prepared and really wanted the work to stand on its own.
And so what was your, what did you present?
I presented an improved power forecasting model, and it was actually this poster here.
For those of you listen to the audio, you're missing out again.
Yeah, so I think we're going to try to get up a PDF of all the documentation on the poster. But for those that were not there live too, you also miss out a little bit, because we actually, in addition to all the information and the algorithms that were on this model, we actually did a couple of embedded electronics into the board that were pretty cool.
Major electronics made the mathematics run live instead of just running on a piece of paper and all that other stuff. So we were running the math live with this poster.
Something that occurred to me even before the event was that you have all of these different mathematicians and industry experts coming into this one gathering, but for the work that I've done, and for really the work that everybody individually had done, they were the expert in that field. And it's not something that I go and look at other people's work, and I can understand some of the fundamentals of it, but because I don't understand that industry or that particular direction that they took the math, it becomes a little obfuscated in the jargon of that field.
It's not like programming where you can sit down with the code and 5 minutes understand what's going on. You got to really know what methodologies they use. I mean, there's so many different mathematical methodologies out there. People were asking us, what's a PID controller? And we know what a PID is because we do a lot of robotics, but apparently that's not a...
Yeah, a lot of control theory doesn't make it into every other type of math. So if you're looking at the numerical theory, group theory, any kind of stochastic prediction, or your eigensolvers, you're not necessarily going to be familiar with playing around with control theory. And so that was actually a new thing to a lot of people who were there. In addition, some of the terminology, like static load, depending on what industry you're in, actually means pretty significantly different things.
And that's something we didn't fully know when we went in there. That was kind of...
I know what static load means in terms of the power industry, but for other ones, and so there was a little confusion there among people of, well, what does static load mean? And we were there, so we were able to explain that. But I think it's interesting. It's almost like even if you're speaking the same language, you're not.
Yeah.
There's that trying to bridge that gap to the other industries and other fields, and really that's why we did the electronics embedded in it. It was to break it down to a point where people could actually experience the math and have kind of an intuitive understanding of it, as opposed to just looking at the algorithms, which are, if you're not used to looking at it, I really would challenge people, well, how would you visualize it in your mind? Do you plot a spreadsheet graph when you're thinking of it here? And I don't think most people are going to have that, sort of math superpower.
I know, because we were right next to one on neural networks and then one on predictive loading or virus loading with censored data. And both of us are sitting there looking at them like, that's really cool, and had the guys explain it to us, and we kind of started getting it after they explained it. I think that's the big help, is when they're, other people are able to explain their work really well.
Yeah, and I'm gonna admit that there were some posters that were just, the people weren't there. They weren't there to answer questions about it. I understand some of them were actually in another country, so they had just sent their work to be posted up. I was like, I could understand portions of it, but I'm sure if they were there to represent their own work, that it would have been a little better understanding. And that was the exciting part for us, honestly, being our first time doing something like this, was getting to meet the people and getting to see their reaction to the work. I think one of the biggest parts of it for me was actually having a couple of individuals who really took their time to go through every little piece of the work and try to pick it apart. And in the end, they were leaving pretty satisfied that it was a solid piece of work. The assumptions that were made logically and for a particular reason, not just so that I could make it easier, but to better highlight the usage of the PID control loop as part of the model.
Yeah.
So
I was really worried for you, and I know you were nervous that it was going to get, just laughed out of the room with, all of the, we were looking at it going, it's, pretty simple math. It's just like, first year engineering student math here, but,
Yeah, well, and this entire model was actually running on, an Arduino. It's running 16 megahertz, 8-bit. A little bit of programming trickery was done to make the float point work. And yet, I feel that we actually got a really, really positive response on that. It's actually encouraged me to proceed further with the work, and I think that the next step with this, like Scott Little's, is going to be to produce a paper of this work.
Yeah, we can get, just a little more data and, play around with it, for some other areas. But, that's definitely, something, to pursue with that. I was, really impressed at the SIAM conference at just, how friendly the people were. And, they came up and talked to us, and we were able to, talk about other things and, even on their level, talk about stuff. That was, for being our first, time in this thing, because we're not exposed to it, through academia.
Yeah, I got to say, a very welcoming crowd. I met quite a few people at some of the sessions. Definitely some great speakers there. We had the John von Neumann lecture, was actually one that I had attended. And
that was the one by Stanley Osher?
Yes.
Okay.
And that was what sparsity and L1 optimization can do for you. And I definitely encourage anybody who's listening or watching to go look into his work a little bit. It actually was something that related to the work that I was doing, and I saw it as a potential improvement to some of the process used here. That I use the Fourier transform, and then I do a hard shrinkage of the values on the Fourier transform to identify the significant contributors to the wave.
So you needed a little bit of compression.
Yeah, I couldn't use everything because that would be an overfitting of the data and would have been problematic. I actually needed that clipping, that compression. And his talk was focused on more towards video compression methods and using the L1 optimization, so a soft shrinkage of the wave. But would certainly, I would see that method being applicable to this work as an improvement to it.
Yeah. I mean, that's one of the cool things, about what we do is we try to expose ourselves to as many different fields as possible because you never know where you're going to find a tool that, fits with something you're dealing with.
And it really goes back to that talk that we had. I don't remember how many podcasts ago that was.
Not that many.
Talking about the tools and how having a variety of tools is important.
Yes.
Honestly, video compression is not something that I deal with.
Yeah.
Or even dealing with those kind of numerical compression methods.
Yeah.
It's not something that I really have been very exposed to, even if I understand, the basic premise of it and why it's good.
Yeah.
I mean, certainly putting for uploading video, we use video compression.
Yes, we do. I know I talked with a few people about parallel processing and stuff like that, and how to get some mathematical things done in parallel versus serial processing. And I didn't know that some of these algorithms become cumbersome, like almost impossible to actually convert to massive parallel processing.
Yeah, and that's actually one that another talk that I went to later that day regarding eigensolvers and some image manipulation was actually, that was one of their biggest concerns, was the processing power required to run the algorithm properly, and that it's only in recent endeavors, and they were talking about using some pretty serious computing power, and that it was still taking many seconds to run through the image manipulation that they were doing on each frame.
You mean many seconds, or is this many seconds adding up to minutes, adding up to hours?
Yeah, well, if you've got one image, you're talking seconds here. If you have an entire video, you're talking a significant dedicated amount of time, and on a powerful machine. And that this was actually math that was developed back 12 years ago, and how he was talking about how the parallel processing and the computing power was making it more feasible. But I think that the programming methods, there's probably still a lot of opportunity to develop in those areas. Try to streamline, optimize, and improve these algorithms so that they can run more efficiently. At the same time, having an improvement of the computing power is important.
Yeah.
That's something that, kind of I think we innately know, but, talking to these people that are really pushing the limits of these image processing and manipulation and compression methods, seeing these people that are getting the most out of those computing cycles, it was just really fascinating experience. And I don't think there's, that many opportunities where you're going to get to learn from, these kind of experts in the field. People were coming from all over the country. They were coming from all over the world, really. So, it's a great culture exchange, and you get all these different perspectives that are experts in their field. And I think I can't really stress that more, that meeting these experts in their field, they have something, pretty huge to contribute to a group at large.
Yeah, they were very dynamic. It made it really nice, the fact that all these people were there, and it wound up being better than saying, like, if we went to an industrial conference just on power modeling, where everyone there is a power modeling expert. This was experts in all different fields, and kind of allowed for a lot of real collaboration. We had some guys that were doing weather forecasting that's able to fit in your model, and they want to collaborate.
Yeah, well, that was actually, still kind of staying in the same field in a way, still in the forecasting, that's this person's passion. and I've certainly taken a great interest in forecasting. But he had a lot to offer, and he really was interested in the work. And from there, that, could develop that relationship. I'm going to be, trying to contact him and talking to him and a few other people that I met from the SIAM conference. But I think really just you wouldn't get that if you were just for the power modeling. I mean, honestly, this power model is a little different. It's not typically how things are done in terms of power forecasting models.
Yeah, but I mean, that's how things are done at Madfellum. So we're always being different and unique and trying to think outside the box.
Yeah. A little hungry, I guess. But
yes.
No, I mean, it really does come down to, not even all the time knowing enough about the particular field that we're working on that, we don't know what the rules are, and that, doing it in such a different way, that's so completely out of the box that, we don't even know where the box is, because we never knew where the box was in the first place on this one.
Yeah.
The power forecasting, when we first sat down and looked at the problem, I remember you and I had this conversation of, well, how would we even begin to go about trying to predict the power usage in an area?
Yeah.
And
we didn't have the statistical knowledge, behind us for, doing the full-blown statistics and, future prediction that you would say do for stock market analysis.
I've got about the statistics knowledge of an engineer, as opposed to a PhD level, statistician.
Yeah.
Or one of the quants doing the stochastic methods for it. And those are very common methods that get employed in power forecasting. You see some, to my outward impression, I've dealt with neural networks setups before. And but a lot of the power forecasting goes that route. And to me, and I think this came out in our discussion, was that we don't like methods that you can't understand why.
Yeah.
Or that you have no ability to test the whys.
Yeah, like what kind of equation would would fit this data without having to do anything with the data itself? What is the best equation to model and produce the same result? That's kind of the method we went. That's why, the PID came out, and because found out very quickly with that it kind of models humans pretty well. It was based off humans in the first place.
Yeah, the original founding of PID was, to follow, the work of a helmsman.
Yeah.
Steering a ship. And so it models how, that process there, but it's also found through perceptual control theory, field of psychology, that people actually fit that kind of control loop.
Yeah.
Very well. And pretty predictably as well. It takes a little bit of group theory into account as well. And so really looking at it as a, who uses power? Well, people use power.
Mm-hmm.
If there's no people there, they're not running the factories, they're not running the stores, they're not doing things in their house.
Well, not if robotics have anything to say about it.
Well, but hopefully, it's not the robots taking over and
but then that's
they're
pretty
just running
predictable.
themselves.
Yeah, robots.
That should be something that's also predictable, even if it were. But for the real world case that we're looking at now, it's people are the drivers of the power usage, and so modeling how the people behave and why they do things, why they react to different things, like in this case, temperature, was crucial to this model.
Yeah.
And it actually fit extremely well, in my opinion. I feel that the assumptions we did to focus on the people allowed us over a 90% modeling just with the control loop. Throwing in some of the Fourier transform and some of the static load, we were actually able to get a 96.7% accuracy, and that was a prediction for 2 weeks for every hour.
Yeah.
So 336 points of prediction, and you're only off by 3.3%.
That's at the end, yeah.
Yeah, I think that's actually a pretty reasonable prediction. Some other models might actually be superior to it in terms of total accuracy, But this is a very beginning model, and I think it's a place to build off of.
So if you're a mathematician listening in the power modeling industry, give us a contact. I mean, that's, we'd like to at least, compare notes and see where we measure up to.
Yeah, I actually did meet a fellow at a university in the country of Georgia who does this kind of work, and he was requesting that I actually collaborate with him on this work, and that's pretty exciting.
Yes.
Right there.
Had a guy from Sandia Labs talk with us. That was kind of an interesting conversation. There's went more the computer science and programming.
Yeah, well, there's definitely a lot in that, and actually, I want to take just a couple moments to just talk about the electronics of this one.
Yeah,
I'll mostly let you go ahead and do that. You had a large part to play in the development of the electronics for this project.
Throwing it together for this project was pretty simple because I've already put in the code together for the book Pro Arduino. I know that's a horrible plug for Pro Arduino, but
yeah, if you haven't bought it, go ahead and pick up 2 or 3.
Yes, 2 or 3. Add 7 to your bill. But it was an Android. It was a Nook Color that we used as a display screen, based on a chart engine, actually called a chart engine. It's a library that you can develop graphs on the Nook or Android devices pretty simply. And then we were running the Android ADK. The Arduino Mega that has the USB host built into it. And then we had, just some simple potentiometers that, measured an analog value, that output, did the math, then output data to the Android device. And then we had a thermodynamic model using RGB LEDs that would...
and that's probably my favorite part of the board, just because it's really great blinky.
Oh, yes, it's definitely a great blinky. It's going to make an awesome mood light when we, tear this, poster down. Well, not tear it down too terribly much, which is enough to get on the wall because it's got a lot of stuff back here.
Yeah. And...
for you on the video, it's a thick poster. And so
that actually presented a problem as we found out we didn't have a table or an easel that we were putting this on.
Yes.
It actually had to be mounted on the wall. That was
yes.
Certainly a lot of tape went into mounting it onto the wall.
Yeah, if you think you're going to be doing these poster sessions or mathematical conferences, remember if non-academics, because I'm sure academics know what a poster is and it always goes on the wall, but you get a thumbtack board to put your poster on.
Yeah, that was one we didn't necessarily expect, but then we didn't ask either. Probably little 4 research might have been good. We still would have done something.
Yeah.
It might have been a little flatter.
Yeah, we didn't. It still would have been 3-dimensional. Would not have been well, I know the physicists are going to argue with me on the paper thickness, but
but I think the just getting the blending of the light, it made it very intuitive. This math down here for the thermodynamic approximation.
Yeah.
I'm outputting, so we have the temperature in one field. We have the thermodynamic forcing, the Q.
Yeah, it really
represented
showed
in the center panel. And then we have the error that's generated internal to the building.
Yeah.
Is the third panel.
Yeah, really showed the how houses really work with the dynamic of the wall and the insulation and everything, and then you have your HVAC systems with the outside temperature, and that's really what we were measuring was the output of the HVAC system.
Yeah, and so people were able to in a pretty big way be able to come up, look at it. Well, what's this? And just looking at it for a few seconds and explaining that's the thermodynamic model. This is what's happening in the real world, represented in LEDs. And it was just kind of that aha kind of moment. It created a simplicity for it that was really great.
Yeah,
and fun for a lot of people because then they see, hey, I can implement my stuff with this. How did you guys implement it? Well, I think we had as much interest in some of the math as people were like, wow, how could I use this for my math?
How do I use this?
And so we really got to introduce a decent number of people to, you got to look up Arduino because there's a lot of things that you can represent.
Yeah.
A little bit of robotics, a little bit of lighting, that you could make something really interactive and intuitive
Mm-hmm.
like we attempted to do. As far as the PID control, being able to go and manipulate the gains, uh, really, we had some people that were playing with it. They seem to want to see what does it look like at the extremes of the thing.
Yeah.
I know the settings, so I was able to set it pretty well. And they were able to live see that this model was actually, in fact, doing something. It was actually working.
Yeah.
In terms of being able to predict the power usage.
Mm-hmm.
And in that way, how user simple it could be.
Yeah.
Certainly being tuned by a machine learning algorithm is probably going to be, that's the method that we went with for the actual production of this.
Yeah. So one that was the big thing I was going to add a lot of cycles was the machine learning. But as far as once it's tuned, it runs on an 8 megahertz, your 16 megahertz 8-bit system fairly decently.
So, considering we were getting in 2 weeks worth of crunch done in a matter of seconds, I think you could run it on an 8 megahertz too. But
yeah.
And that wouldn't be a problem. I mean, once the math's up and running, it runs good. It just takes a little bit more setup, is all. So.
Yeah, but I mean, it's still nowhere near as bad as some of the neural networks I've seen that were set up. But I think it'd be a good idea if we do like a tutorial teardown of this, for anybody who wants to see it. Go through the kind of how the LED thing was made, because that was actually made with tearing apart LCD screens. Kind of pulling the good old maker.
A lot of recycle and reusing.
Yep.
So.
Well, yeah, we did some reducing too at the same time.
Yeah.
So, but yeah, I think that's good enough for today. So we should probably call it.
Well, SIAM was definitely a great event. We'll be there again.
Yeah. And encourage anybody who's thinking about any kind of math engineering, definitely check out SIAM, because I was really impressed. I mean, it was better than Interop or some of those other industry ones that we've
you don't get so blinders on for the industry. It really is an eye opener.
Yeah,
seeing all these different lines of thought.
This has been All the Ideas here on madfellowstech.com. If you have any ideas that you'd like to hear us ramble about, email them to alltheideas@madfellowstech.com.